So, is my screen visible to everyone?
Yeah.
Okay, let me.
So I'm very pleased to welcome our resource person, Dr. Manish Kumar of Oil India Limited. He will be speaking on the very important topic of upstream petroleum sector, the water injection. Dr. Manish Kumar is currently working as DGM Reservoir Subsurface Manager, Eastern Asset, Oil India Limited, Yoganatha. He did his BTech from the Department of Petroleum Engineering from Indian School of Mines, IIT, Dhanbad in the year 2003, and PhD from the University of Petroleum and Energy Studies in the year 2019. He has published several research papers in national and international journals and conferences. His research interests are enhanced recovery, field development planning, well testing, and reservoir simulation. So please join me in welcoming Dr. Manish Kumar. Over to you, Dr. Kumar.
Yeah, thank you, Dr. Phugan, for the introduction. So today I will be talking on the topic water injection. I request listeners to mute themselves. I think there is some issue in the it is reiterating. So the outline of the presentation starts from the stage of recovery, and it will go from water injection till move to water flooding, and what are the factors that are important for water flooding, what are the patterns, followed by water flood screening, sources of water quality, effectiveness, and lastly conclusion. So in this slide you can see there are several barrels which have been placed. The first barrel that is in place represents basically while in place, and you can see a number is represented there, 366 mmSTP. And in primary recovery, that the 25% recovery is obtained, that is equivalent to 90 million barrels. And if you go for secondary recovery, it is equivalent to 155, and if you go for tertiary recovery, it goes to as high as 235. The same thing has been represented on the diagram below in a field while rate versus time. So today we will be talking on the secondary recovery technique, and the one of the technique of the secondary recovery is water injection. Although gas injection is also a technique for secondary recovery, but we will talk mainly on the water injection part today. So now we need to define what is water injection. Basically, it is a secondary process by virtue of which we try to increase the production from oil reservoirs. So I want to bring your attention to the bottom graph, where you can see there is a graph where representing on y-axis it is reservoir pressure, on x-axis it is time, and you can see the line, the orange line, orange solid line. It is representing the decline in the reservoir pressure, and there is a blue line which indicates that this is a point where we are initiating the water injection. So what I mean to tell, if we try to produce oil and water and gas from a particular reservoir, this reservoir pressure depletes, but we need to know when we should start the water injection. So the mainly two factors are important in this aspect. The first is the pressure should be greater than hydrostatic pressure, and it should be greater than bubble point pressure. For the knowledge of house, I will just reiterate the definition of bubble point pressure. It is the maximum pressure at which the first bubble comes out of the solution and goes out. So we should avoid the reservoir pressure to reach bubble point pressure, and start initiating the water injection before the bubble point pressure. And at the same time, the pressure should be greater than hydrostatic. Let's take an example of a well which has a depth of around 3000 meters. So if you calculate the hydrostatic pressure, the gradient is 0.1 ksc per meter. So that way the hydrostatic pressure will be 300 ksc. The reason why I am pointing towards hydrostatic pressure is, if your reservoir pressure is not greater than 300 ksc, it will not be able to live the amount of water that is being produced. So these are the two important factors. The first one is the hydrostatic pressure, and the second one is the bubble point pressure. These are the two important things that is required for the initiation of the water injection. And the purpose which is being served by the water injection is voidage replenishment. So injection of water to maintain the reservoir pressure and displacement of oil by water from the pore spaces is basically accomplished by water injection. Now I am a little bit deviating from the topic of water injection and trying to define a term from EOR, that is low salinity water injection. This is the same thing you might have heard several times about this term low salinity water injection. This is nothing but generally the water we are injecting into the reservoir is from the produced water. If you are taking water from your water table or from river, the salinity is low. So to quantify the salinity, I can take an example of your drinking water. Generally, the salinity of drinking water is less than 100 ppm, or it may go as high as 200 ppm. So if you are injecting this low salinity water injection, it acts both the purposes. It replenishes the voidage replenishment, increases the reservoir pressure, and at the same time, it also acts as a EOR. There is a mechanism for LSWI, which I am not going to deal in detail, but just to brief it, it reduces the residual by saturation basically, which is the primary target of any EOR, and it can be quantified. So in Oil India Limited, we have tried to quantify it, and we have seen that the residual well saturation has gone down to a level of 5.9, and that is approximately 6%. So this was a glimpse of what is low salinity water injection, what it does. And on right hand side, you can see a table which is depicting different EOR methods. So this, you can see that low salinity water injection is a designated EOR technique, and it, as per EOR policy that has been given by Directorate General of Hydrocarbons in year 2018, that has been just given in a blue line. You can see it. So that's way water injection is serving both the purposes of pressure maintenance as well as EOR. So I have shown you the low salinity water injection. I will be giving you some field examples also in the end of the presentation. I have got two examples of two different fields where you can see how it has impacted. Now, as I have already told that we need to do water injection, and there is a criteria for doing water injection. The first criteria was the pressure should be greater than bubble point pressure, and it should be greater than hydrostatic pressure. But why should we inject water? The primary objective is to maintain reservoir pressure, that is the pressure maintenance, and the second is the supplement natural water influx. So as you know, if you don't inject water in any of the reservoirs, even though there is some amount of water that is being produced, while alone is not produced, water also comes. So the water which comes without water injection is basically coming from the natural water influx. It is the energy of the reservoir which comes of its own by supplementation of natural water influx. So these three things, like maintaining reservoir pressure, increasing reservoir pressure, and supplementing natural water influx, these three things are a requirement of any water injection. Now there is a potential of water flood. So if you can see in the middle of the column, you can see the primary recovery ranges. You can see in water drive, the bottom row, you can see water drive that has got the maximum recovery factor. It ranges from 35 to 50%. So I was talking about the natural water influx. You can see if there is a natural water influx in the form of a water drive, the recovery can go as high as 50%. And as you go on reducing the drives, like if you go only in the fluid expansion drive, you can expect a recovery of 3 to 10%. But generally, in any of the reservoir, there is a combination drive. Gas cap is also present somewhere. Somewhere water is present, and somewhere gravity also plays a role. So definitely, the primary recovery that we obtain is a combination of all this, and we get a mixed kind of recovery. So you can see there is a potential for water flooding where we can do water flooding. The solution gas drive reservoir is a potential for water flooding. It's a good. And also in your fluid expansion drive, both are ideal candidate for doing water flooding, or let's say water injection. In water drive reservoir, since there is a natural energy influx and the water comes of its own, so there is not much requirement. But in solution gas drive, definitely there is a requirement of pressure supplementation, and it's a good candidate. Now to illustrate more on this, I have given an example. So in this graph you can see there are primary vial and the secondary vial. The primary vial is shaded in the texture part, and the secondary vial is even another shade. So you can see this the secondary vial that has been obtained mainly by doing some supplementation of pressure. It can either be through water injection or it can be through gas injection. And you can see the different periods, like when we have started the injection. So the number A, you can see an alphabet A, this is the initial fill-up period. So to give more illustration on initial fill-up period, let's suppose you have got a reservoir from where you have started the production for 5 years. So there is some void that has been created, and you have not started your water injection from day one. So definitely there will be some gap that has been created in the reservoir in form of porous spaces by production of oil, water and gas. And you can see there is a decline in pressure. So if there would not have been any decline in pressure, so this initial fill up should have been done by natural energy. But now you can see that the reservoir pressure is declining, and the injection has been started by the first dotted line. So if you see the part A is the initial fill up period, and after that there is an increase in the production by secondary vial. So you can see clearly by implementation of secondary recovery technique, that is water injection, there is a gain in vial production. So this is a typical representation of by a particular reservoir where you have initiated water injection after a certain point of time, and then the reservoir responds and there is an increase in production. So just try to look into the future where what might happen if you are having a depletion drive reservoir and your water drive is not that much strong. So in the top figure you can see the initial oil water contact, and the wells have been drilled. There is no production. But after some time you can see the oil water contact has moved up, and you can see the representation on the right hand side that oil rate has declined, water cut has gone up, and GOR is flat basically. So this is only because there are two drive mechanisms that is acting on it. The first is a gravity drive mechanism because it's a dipping reservoir, and the second thing is there is a natural water influx by virtue of which this water is encroaching towards the perforation of the bottommost producer wells. The second instance you can see in the edge water and the bottom water, vessel water or bottom water basically. So if you can see in edge basically, edge water drive reservoir, the one end is blocked basically. One end is blocked, but in the bottom water drive reservoir, you can drill in any of the wells. You can even convert the producer well to an injector well, but that facility is not available in edge water. Let's suppose if you want to convert this, if I can get an option to draw, if you want to convert this particular well into an water injection well, that is not possible. But in bottom water drive reservoir, there is a flexibility. So this well can be converted to water injection well, but this well cannot be converted. So in edge water drive reservoir, there are typical characteristics. This well will be watered out on a very first instance, because water will be encroaching in this direction, followed by this, and lastly this. So this well will be this particular well will be giving almost clean, while what I can say, to a maximum production history. But these wells, this particular well will be watered out very soon, and this will be following in the similar sequence. So let me know if there are questions in between. I can take the question in between. Otherwise, I have dedicated a different time slot for taking the questions from all the attendees. So you can interrupt whenever you want to do so. Okay, I have to erase it. So now we'll see how does a water flood work basically. So as I have told in the previous slides, some wells are converted to water injection wells, and I've already told that there is a flexibility of conversion of production water to injection wells in bottom water drive reservoir, but that flexibility is not present in edge water drive reservoir. So other oil wells remain as producer, and the injector water displaces or pushes oil to the producer wells. This is a concept of basically water flood. So if I can show you, if you can see this particular diagram, I am talking about this particular diagram. So you can see how this water injection, this all the wells, like these are basically water injection wells, water flooding wells basically, these wells, and these wells are producer wells, producers. So you can see how this water has been injected in a whirlpool, and water is expanding, and it is trying to push the oil towards the producer well, and it is getting produced. So water flood is acting in two way basically. It is increasing the reservoir pressure, as well as it is trying to make a push of this particular oil. This is oil basically. This is pushing into the producer wells. And the second, if I take a cross section of this particular image, I can point out on this image where you can see this is the injector well, and this is the producer well, and this is the oil column basically. You are injecting water in a oil column, and this is how water is moving, and it is trying to push this oil towards the producer well, and it is getting produced at the surface. So there is a slight difference between water flooding and water injection, and I think this is the right slide to illustrate the same thing. You can see that in water flood, you are injecting water in oil column, but if you see this particular injection in this particular well, this is the color that is marked in blue. This is basically represents nothing but water, and this black part is oil. So you are injecting in the water column only, and this is oil. This black portion is oil basically. So you are doing a pressure maintenance, and simultaneously there is still some layers. The layers can be in these directions also. If the layer is like this, if I try to draw the layers based upon the bottom layers, the water will try to follow this path. And if you can see, it is trying to do flooding mechanism is also being applied. Even though you are doing water injection, but some kind of flooding is also being applied, because water will not move horizontally. It will try to move in a particular layer. And according to the depositional environment principle, this layer will not be this layer has been deposited at a particular angle. So this is the particular strata that it is following basically. So this will the preferential movement of water will be definitely in this direction. So interchangeably, I will be using the term water injection and water flooding, since if you have got a horizontal bedding plane, which is being explained in this particular image, then water injection will do only pressure maintenance job. But if there is a dipping plane, it will the water injection will act as a water flooding. So I think I am able to explain the term water injection and water flooding, which is very important. And let me know if you have some questions on this. Now, there are various reservoir factors to consider for a pressure maintenance or water flood. The first thing is reservoir geometry. What is the geometry of the reservoir? And lithology. What is the porosity, permeability, all those things. And then the fluid properties and relative permeability relationship. And lastly, the pressure performance. So we will try to go one by one for each particular factor in detail. The first thing is reservoir geometry. Reservoir geometry is nothing but it's a structure or stratigraphy that controls the location of the wells and to a larger extent dictates the method for producing a particular reservoir. So reservoir geometry, if I try to depict in a detail, I have to go to the previous slide. So you can just consider this you can take this cross section and if you can see the bedding planes. This is almost following the top of the structure basically, and this is the injector and then this is the producer. So there is no dip basically, and even if there is a dip, it's a very gentle one. And there are different kind of structures. I think you all might be knowing, like anticlines. This is the typical anticline. Like syncline is also there. Some faulted structure is also present. Like suppose you have a dipping structure and a fault can cut it through. So this particular part might go this might go in the upward direction and this go in a downward direction. So it will definitely impact. So by virtue of reservoir architecture, I mean to say there can be different architecture of the reservoirs. It can be anticline, it can be syncline, it can be a faulted reservoir, and it will also deal with the fault. What is the throw of the fault? Throw of the fault means if I try to illustrate in more detail, we'll just draw. Let's suppose there is a fault, and the thickness of this particular bed is around, let's suppose, 10 meters, and this particular part is around 2 meters approximately, and let's suppose this is also 10 meters. Now just think of what are the chances of this particular wire in communication with this particular part. If these two parts are not separated by a particular, this is not a cell. If there is not a cell barrier, then this particular wire will be in communication with this, even though there is a throw of 2 meters which is separating it. So this wire will be in communication with this one. So all these things, like your structure, like anticline, syncline, deep of the bed, fault, the presence of impermeable layer over the faulted layers. All these come in the reservoir architecture. Let's try to keep an water injection well. If I am keeping an injector well in this particular zone and trying to inject it. So if this is in communication, then the pressure will try to migrate, or let's suppose this while while will be migrating in this direction. You are trying to push it from this direction, this will migrate in this particular direction. So this should be in isolation. So reservoir architecture is very much important, and to know the reservoir architecture, the best thing is you should take the help of seismic, whether there is a fault pattern which can be seen or not. And if you have seen the structure contour map, it clearly depicts what is the how much is the isoplate thickness, how deep it is, whether a throw is present or not. So all these things are present in a structure contour map. Now coming to the lithology. So lithology basically it depends on there are three terms which are very much important. First thing is porosity, second thing is permeability, and the third thing is clay content. Porosity, by definition, everyone knows porosity is nothing but porous space that is available in the between the grains, and the permeability is the ability of fluid to pass through it, and the clay content is nothing but the silt percentage that is present. So you all these parameters like porosity, permeability, and clay content, all these things can be measured directly or indirectly. You can measure porosity, permeability, and clay content in a laboratory. If lab data is not available, you can take help of logs, well logs. There are some logs which can measure permeability, but the porosity and the clay content can be measured by your, let's say the most simplest of log is, in earlier time it was SP, and currently it is gamma ray. So by using gamma ray log, you can estimate porosity and clay content, and permeability you can estimate by a porosity permeability transform. But if you don't have some sonic logs available with you, so porosity is directly relates to the total oil recovery from a reservoir, and the reservoir of permeability controls to a larger degree the water injection that can be sustained for a specific sand phase pressure. So if there is no interconnectivity, let's try to give you an example. Let's say this is a reservoir, and I am keeping this is an injector, and this is a producer. I am trying to inject by this particular area. There are several layers present, and if you see that the layer in which I am injecting has got a, you can measure all the properties on this well scale only, at this scale and this scale. But what about the heterogeneity between this injector and producer? You are not knowing. So the estimate of porosity and permeability is generally done on a stochastic basis, and you are trying to estimate what might be the porosity or permeability between these injectors and producer. So you are trying to inject in this particular zone, considering this is your base zone, very clean, and the water should go through. But what might there might be some small barriers. The percentage of shale has increased. This is, let's say, suppose this is shale. It will not allow to move the fluid to pass through it. Rather than fluid will try to move and choose this direction or choose this direction basically. So basically, permeability can be measured on a well scale, but the interwell connectivity is very much important, which is not known to us, and this is totally on the stochastic measurement. And what is happening inside the reservoir is least known if we are trying to just inject in a particular formation and we are not seeing in the producer. So the interconnected permeability is very much important from the point of view of injectivity. And porosity is the parameter which is important from the point of view of basically in place recovery factor and high withdrawals. But the permeability is the main important element, and permeability deals with the clay content also. If it is the reservoir is having a very less clay content, then the permeability will definitely be reduced. And it is a very, if the clay content goes on a higher side, the permeability will be decreased and vice versa. Now coming to the fluid properties. So there is one very important parameter, that is mobility ratio. The mobility ratio is nothing but mobility of the displacing fluid to that of the displaced fluid, and ideally it should be less than 1. So what might happen, just give me a minute, I will draw again the same thing. This is an injector and this is a producer. Basically what might happen if I am injecting from this particular zone and the mobility is greater than 1. So what might happen, this particular water, this is, let's suppose this is in wild zone and this is water zone. So what might happen, water will create a channel of its own and try to reach this particular part, again in this particular part. So it will not try to make a piston like impact. So if mobility is less than 1, this particular this particular partition, this will move uniformly at time t is equal to 0. Let's if this position is here, so at time t is equal to t1, this the position will be here like this. So there will be piston like displacement if this mobility is less than 1, and if it is greater than 1, definitely this injection water will be break through in the producer well very soon. So this is the definition, and if I can write, mobility is equal to permeability divided by viscosity. So this is the K by mu of the displacing fluid. This will be for water, and divided by K by mu of oil. So it should be less than 1 basically. Now the another factor that affects the mobility ratio is the relative mobility of the reservoir of to the displacing and displaced fluid. So these are the two important terms which are important from the point of view of water injection. Now coming to the pressure performance. Now the reservoir pressure in the water flow should be held higher than the saturation pressure to maintain the pressure close to the initial pressure. Now if I have dealt in detail on a very first slide where I have told that reservoir pressure should be greater than saturation pressure as well as the hydrostatic pressure, and now I am trying to tell that this pressure should be close to saturation pressure to maintain the pressure close to the initial pressure. So the term, the saturation pressure is very much important, and the initial pressure is the pressure when we have drilled the well and tried to take the static bottom hole pressure or take a pressure build-up survey. So our main objective from a layman's point of view will be that they should be meeting two objectives. The initial pressure is known to each and everyone. In absence of any PVT properties that is being taken on a oil and gas sample, we can know that this particular pressure, the saturation pressure, that is also known as the bubble point pressure. But if it is not known, you should keep in mind that the initial pressure should not be declining much. If it is declining much, definitely the lifting capability of the reservoir by virtue of its own energy will be reducing. And if I just need to mention one more point, suppose this is a well and this is a wellhead basically. So it is not always possible to take a static pressure, that is PS, or as BHP you can tell. But on the top, on the wellhead, you can take tubing head pressure. It is very easily available. So it is very imperative to see whether your THP is declining or not. So if your THP is constant and your production rate is also constant, then there is no worries. But if your THP is declining, then if you need to take measure this static bottom hole pressure. And if you're not able to measure, then you should do some correlations. You can take THP and you can use some correlation, the vertically flow correlations, and try to add and reach up to this particular point. You can estimate this PWF and have some estimation. So this pressure is very seems like it's a very easy task to measure the pressure, but their implications are much. Going off the context, let me give some more information on that when the tubing head pressure, what it might represent. So you might have heard about the Christmas tree and the blowout preventer that is being that is being kept on top of any wellhead basically. So every wellhead or BOP or Christmas tree has got a certain rating. So if your tubing head pressure is uh, is very high, let's suppose it's in the range of 5000 psiz, so you need to be a little bit cautious, because in While India Limited, what we adopt is we have got two different kind of wellheads, and the one is of one the rating of one wellhead is around 5000 psiz and the other is 10,000 psiz. So if your tubing head pressure the suggests that the pressure is close to, you need to replace this, otherwise the well is unsafe. So this is out of context basically, but this thing I have noticed quite often. And if your tubing pressure is high on the higher side, definitely you should have to do a workover, kill the well, and after that only you can replace this your wellhead. So by I just so want you to concentrate on this is how significant it can be. Just looking at a particular valve or gauze, you can take a major decision in a well operations and do some prevent some unsafe practices. So apart from the sustaining the pressure to saturation pressure, to bubble point pressure or initial pressure or hydrostatic pressure, there are other factors also, like oil price. So right now, I think many of you are looking at the soaring oil prices, and it is right now at a level of around $128 per barrel or $130 per barrel. I think it's the highest oil price since last 7 to 8 years, as I remember. The marketing conditions, operating expenses, the availability of water. The water availability is also a major issue. So from where you can get water? In most of the oil fields, the produced water is treated, cleaned, and then it is made available for water injection. Legal considerations are also there, such as minimum spacing and adjacent leases, basically pattern selections and process considerations such as injection rate, response time. So let me give you some more time on injection rates basically. What might happen if you are injecting at a very high rate? What might happen, and how you can determine whether a fracture has happened or not? So there is a plot called Hall plot, by virtue of which you can tell that whether this water that is being injected into the a particular well is not fracturing the reservoir. So injection rate is also very important. Response time. You are injecting in a particular injector well, and the producer well is around 200 to 300 meters away from this, and you can see what is the ideal time that there should be a change in salinity. So let me draw a figure again and give some illustration. This is injector and this is producer. So you are injecting in this particular well and you are trying to produce from this well. How you will come to know that the water that you have injected has reached this producer or not? Because see, either you can use tracers, or if the tracer is not available, you can measure the salinity of this particular water. Let's suppose the salinity of the produced water injectors is around 500 ppm. And in producer water, the salinity is around 4000 ppm. So the day you are seeing that this 4000 ppm that is obtained from the produced water is reducing in a particular trend, or the water cut of this particular producer well is increasing, you may get some indication. Second thing is if the reservoir, the pressure, the flowing pressure, the PWF has increased. It might also give you some indication basically. So these are the some indications of seeing the interconnectivity between injector and the producer. You can look at the salinity, water cut, wellbore flowing pressure. So now coming to the flooding pattern basically. There are several flooding patterns that are being adopted in the industry. That is ideal. Although before showing the flooding patterns, I must tell you that these patterns are textbook examples, and in actual field practices, it is tried that this pattern should be followed, but it is not. In most of the times, this pattern is not being followed because suppose I am showing you an example of line drive basically. So you can see all the bottom part. This is the producer basically. It represents the producer wells. This is the producer category, and this is the injector category basically. So when you have drilled this and this, when you have drilled all these wells, ideally these wells have been producer, and at one point of time you are converting this producer to injectors. It might not happen this the same well, this particular might be available for injection, or it might happen there might be some downhole communication, or the well has some fish inside the hole, or there is some well integrity issue. So in line drive basically, for each producer, just behind it there is an injector basically. It's in the same line. That's why we call it line drive. It's in the same line. Now coming to the staggered line drive, it's just the name. The name suggests. You can assume that for two producers, you have got one injector basically. For these two producers, you have got injectors. So there is a staggered basically. Now this is the flooding pattern, flooding for 5 spot pattern. So you can see there is a producer in the center. There is a producer in the center. There is a producer in the center, and you are injecting from 4 different corners. So you can see it's a perfect orthogonal shape. It is a perfect orthogonal shape. But ideally, the placement of well, either producer or injector, it can only happen in such a ideal condition if your reservoir is non-heterogeneous and layer cake perfect reservoir where you can place your wells. But it might not happen that way. So definitely, if this producer is at this particular position, the producer can be somewhere here, depending upon the structure contour, structural position, its pay thickness, your oil saturation, and the log signatures. So depends basically. So even though this is the 5 spot pattern, and there is another pattern which is the same name, but it is called inverted. It has not been shown. So inverted 5 spot pattern, you can just reverse it. In the center, you will be having injector, and in all 4 corners, this will be injector, and this will be producer basically. So just the inverse of 5 spot flooding pattern. Now same thing is being replicated here. Here you can see 7 spot flooding pattern. You can see 1, 2, 3, 4, 5, 6. 6 producers are there and 1 injector is there. So it's a 7 spot flooding pattern. Again, the 9 spot flooding pattern. You can see eight producers and 1 injector. Now, when you are injecting in a particular pattern, so you can see how it behaves basically. So you can see the shape basically. This is the early life. After that, it is early life where water bank is expanding, and it's in the mid of the life, and it's late in the life basically. So how it is expanding, how it is moving ahead. Now coming to the next important agenda, that is the screening of water flood, the source of water, and the water quality. So you can see there is a process basically for water flood screening. The first one is the macro scale screening. The second is micro scale. Third comes the water quality, water source and quality evaluation, and the lastly simulation and implementation. So I will be going by one by one for all the screening process for this water flood screening and evaluation process. Just give me a minute. Okay, we can continue. So as I was talking about the water sources, you can see the first and very important is the produced water. The water that has been produced from the producer wells that is being re-injected. If I term it in a small form, that is produced water re-injection, that is PWRI. It is the most common of us. And the second is surface water, like the water can be from river or it can be from lakes. And the third one is a shallow groundwater. It is very similar to your water table from where our drinking water comes. And the next one is the best water streams, and sometimes often a mixture of some of the above, because it will not be possible to take the quantity or volume of water that is being required for water injection to cater from a particular area. Like the produced water cannot be the whole and sole part, so it can be supplemented from your surface water or shallow groundwater. It's a combination basically. But these are the water sources that needs to be identified before starting any of the water injection. Now injection water quality issues. So if you are injecting water in an injector well, so there might be some issues. So the first issue that might happen is basically you are injecting water and the water is not going into the formation. Then what you will do? So this is the primary thing that might happen. So there are some quality checks that is required on an injection water. So if you can see there are different contents which needs to be measured and it should not be beyond a permissible limit in any of the injection waters. So the first thing that is known to most of us is total dissolved solids basically. The total dissolved solids should not be greater than a particular amount in the injection water. The second thing that is common is total suspended solids. The next thing is a specific ionic composition. If I take ionic composition, technically the presence of iron should be very less. And one thing which has not been mentioned is the presence of oxygen. So these are two important elements that should be removed before injecting the water into the formation, and the salinity. Oil and grease content is another thing. This particular part comes when you are trying to do remediation work to produce water re-injection, then this particular oil and grease content should be taken care of. And like in previous slide, I was telling about the water sources. So if you started a water injection in a particular reservoir through a water injector, so you should be also ensuring that whether this injection water is reliable or not. Suppose you are taking from 3 or 4 different sources, and whether those sources are sufficient to supplement your water injection requirement throughout the year or not. It needs to be uh, ascertained before initiating, and whether it is sufficient volume for future requirements. Let's suppose you have initiated a water injection in a reservoir where only 2 producers are there and only one injector is there. But later on, when more and more wells will be coming, there will be more withdrawals from the reservoir. And in order to supplement this fluid withdrawal, you need to have more water injection wells. And if you've got more water injection wells, the volume will also be increasing. So depending upon the field development plan, you need to quantify what is the withdrawal rate that is happening from the reservoir, what is the drive mechanism of the reservoir, whether this reservoir is depletion drive or solution gas drive, or it is active bottom water drive. So depending upon drive mechanism, your water injection requirement might vary. So these things needs to be ascertained, that is how much volume will be required for the future. Now successful water flooding. There are some key elements for successful water flooding. The first thing is your high movable oil saturation. Means if you don't have oil saturation inside it, what water can do? If you try to inject water and produce water only, there should be movable oil saturation. Moderate to low oil viscosity. This particular term is being directly dealt with your mobility ratio. If you have calculated the mobility ratio, so it takes into consideration permeability and viscosity of displaced fluid as well as displacing fluid. So if you are measuring or calculating mobility ratio, then you need not worry about the oil viscosity of displacing and displaced fluid. Favorable relative permeability. Next is low permeability variation. Low permeability variation is nothing but the reservoir should not be very much heterogeneous. If the reservoir is heterogeneous, you are injecting water in a particular point and this water is going somewhere else. pattern should be symmetrical. And next to this is ability to inject large volume of water. So the same thing has been dealt in the previous slide, ability to lift larger volumes of reduced water. Yes, and the pumped of producing wells basically. So the last point which is mentioning the pump of producing wells, I don't know it is being understood in a correct perspective from all of you or not. So just let me tell you. Let's take an example of oil well. Let's suppose this is a packer, this is a tubing, this is the perforations basically. Let's suppose on day one your water cut before initiation of water injection or water flooding, your water cut was nil, and when water injection started, the water starts approaching these perforations and water starts getting produced with oil. So it is serving both the purposes. Your pressure is increasing and your fluid inside this particular wellbore is being lifted to the surface without doing any intervention jobs. But what might happen if the volume of water or the water cut goes as high as 90 to 95%? The reservoir pressure might not be sufficient to lift this fluid. So in such cases, if the PI of the well is high, if the productivity index of the well is high, you might end in deploying a ESP pump basically. You have to incorporate a pump to lift that fluid. So this particular fluid can be lifted. Otherwise, the high density fluid inside this wellbore will exert a back pressure on this, and this will prevent the fluid from moving in this part. So if you create a vacuum or drawdown in this particular area, this fluid will be lifted easily. So at the same time, when you are injecting water, you should also have, you know that the water cut will be increasing in the producer wells, and you should have sufficient mechanism by virtue of which you can just pump off all the produced water. Now coming to the effectiveness of water flood, I think that there are two important things, that is the macroscopic effects and microscopic effects. I will be telling both the effects in the subsequent slides. So the macroscopic effects consider these four parameters: the heterogeneity, the porosity, contrast, the continuity of the reservoir, and the fault and the fractures. So these are the things that is on a broader scale basically. If you go to the poorer scale, that is being dealt by microscopic effects. So just let me read out microscopic effects, and then I will try to combine these two and tell you how these two things are combined to make a successful water flood. In microscopic, you are dealing with the pore size distribution and geometry. So I think many of you might be knowing the geometry of the pore. There are various distribution pattern in which your porosity percentage increases or decreases depending upon the geometry of the pores basically. The capillary pressure, which is mainly dependent on the grain size. The less the grain diameter is, your capillary will be high. High capillary will be built and your transition zone will be more. Wettability, relative permeability character, and injection fluid induced damage basically. So all these things is being dealt on a pore scale, and these things on a, you can see, on a reservoir scale. So we start with the macroscopic effects. If the reservoir is not heterogeneous, permeability contrast is not that much, one part of the reservoir is connected to the another part, and there is not, the reservoir is not faulted or fractured to an extent then we can say this particular reservoir is well suited for your any water flooding. But even though these parameters are well and good, and your pore size distribution and geometry and capillary pressure and wettability and relative permeability, these parameters are not helping you out, then you will not be able to achieve a successful water flood. So all these parameters which are listed in microscopic effects are measured in a laboratory basically. So you can, or we can take the lab reports, try to analyze those data and try to come on a conclusion. Whether you can well in advance, you can tell whether water flooding will be successful or not based on these macroscopic effects as well as this microscopic effects. So now I am coming to the different factors that will drive the outcome of a water injection project. So you can see a formula, and these acronyms are known to everyone, even though I have listed what they represent. NP is the cumulative water flood recovery. N is the while in place start of injection, and this EA, EV, and AD are different sweep efficiency. Like A represent for aerial, V for vertical, and D for displacement efficiency. So there are if you consider only aerial sweep efficiency, it depends on various factors like mobility ratio, the pattern that we have selected, this line drive, staggered line drive, 5 spot, 7 spot, or 9 spot, directional permeability. Directional permeability, let me give you some more what is directional permeability. Let's suppose this is a particular reservoir. So I think you all might be knowing this fact that permeability has 3 components. It is permeability in X direction, permeability in Y direction, and permeability in Z direction basically. So this Kx and Ky, most of the times we assume that this Kx is equal to Ky. Means in laterally, if you see, or aerially, if I can say, these two parameters are pretty similar if the reservoir is not very heterogeneous. But sometimes there is a directional permeability associated. Kx is not equal to Ky. So that thing is also to be noted. Let me illustrate you with this example. Let's suppose this is an injector and this is a producer, and your directional permeability is in this direction basically. Then this produce injected water will reach this producer. But what might happen? But this is the case when you know that there is a directional permeability in the reservoir which is in this direction. But if this fact is not known to you, you will try to put this producer here, and you will not be able to see any effect, even though the distance between this injector to producer is more than this distance, even though the fluid will move in this direction and not in this direction, because there is a directional permeability involved in this. So the knowledge of directional permeability is very much important while implementing water injection. Now coming to the pressure distributions. Again, I take an example. This is a reservoir basically, and let's see that if one particular part, in this particular part of the reservoir, you have done drilling of around 20 wells. 20 wells you have drilled, and in this particular part, I'm segmenting it. 5 wells you have drilled, and this particular part only 2 wells you have drilled. So what do you think that the findings will be maximum in this area? provided all are producing with the similar rates. So now, even though I am producing this particular reservoir at the same rate from all the wells, this voidage will be maximum in this area, and the pressure sink that will be created will be maximum in this area. If you compare data of this particular area to this area, so there is a pressure distribution. So this particular pressure will be low and this will be high. So you need to concentrate on this particular part. Your water injection is required firstly in this, then on this, and then in this. So this particular thing is being seen in many of the fields because depending upon the field development pattern or the known data available while drilling or the lease boundaries is specified at the time of the study. The development drilling in one part is the most and in the other part it is totally untouched. So there will be a gap of pressure. So the pressure distribution should also be seen. Cumulative injection and operations. Yes. Now the vertical CP efficiency. Vertical CP efficiency is totally dependent on kV by kH. This parameter you can get from your special core analysis that is being done in the lab. And EVOL, this is the combination of these two, EA and EV. And ED is a function of primary depletion, KR, relative mobility, and viscosity. If we combine it, it is mainly dependent on mobility ratio. Now there is a formula for this volumetric CP efficiency that I have taken for calculation purposes. So you can just calculate what might be the volumetric CP efficiency by using this formula. So these are the various terms like HWC is the coordinate water saturation, HW bar is the saturation at breakthrough, NP is the produced volume, BP is the pore volume, VO is the formation volume vector. So it can just give you an ideal estimate of the volumetric CP efficiency. Now coming to the, you remember when I started the slides that we will be discussing on some case studies, and these case studies belong to Oil India Limited. So for illustration purposes, I am using it, and it can be seen that how water injection has helped in terms of recovery as well as pressure maintenance. I think these were the two things which were targeted when water injection need was required. So just start with the field one. So there are two graphs. First of all, the top graph. The top graph is representing the basically oil, water, and GOR. Oil is represented in red, water in blue, and gas in green. And you can see these black dots basically. These black dots are nothing but pressure trends. So these are the pressure data that have been obtained throughout the life of the reservoir. And I have tried to put a trend line which depicts how the reservoir pressure has declined, how the decline has been arrested, and how this has come forward. So I think if you remember the fill up part, there was a fill up part when I showed you in the second slide. There is a fill up part. So this part can be attributed to the fill up part basically. When there is a arrest in decline and this reservoir borders is being arrested and the void spaces are being filled. I just forgot to mention you in the bottom graph, you can see the water injection basically. This particular curve is your cumulative water injection, and this indigo color is being represented by your water injection rates basically. So you can see if I try to draw a line So this is the initiation of the water injection. From this is the point where we have started water injection, and you can see there is a response. There is some response time. Even I have initiated water injection, there is a decline in the pressure. So some response time is required for pressure effect to be filled. And after that, you can see that the pressure has stabilized. And you can see as we have increased the water injection rates, the reservoir pressure is also going in upward direction. So this was one part of it where we can see that how reservoir pressure has responded in a particular reservoir, how the fill up part has been identified, what is the response time. So all these things can be inferred from this particular field plot. So just look at the numbers basically. So this is an estimation in primary recovery, primary depletion. We could have got only 21%. In water injection, when we did the water injection, it went up to 35%. And after water injection, we have done some EOR method also in this particular reservoir. So I will restrict myself to this particular part only. So even though you can see that there is a jump, there is a quantum jump of around 14% additional recovery factor that has been attributed only by water injection. So this is the ideal example where you can see a reservoir which is producing from 1960s and it is producing till date. This reservoir is still producing, and the current recovery factor is around this 49%. So even though this was a depletion drive reservoir, which is a typical characteristics, the decline in reservoir pressure, there was some aquifer support, but that was not sufficient. So why I am telling this reservoir was a depletion drive reservoir and very weak aquifer support, only because of this particular fact. You can see the blue curves in this particular part. The very minimal water is being produced. Even we have started production in 1958 until 1976, there is hardly any production of water. The water is not being produced. Water is not present. This is the only technical water that is being produced from the reservoir. After that, when water injection is started, you can see how this water volume of the water has increased. Again, when we ramped up the water injection, this water injection has increased. So this is a perfect example where you can see even in the depletion or solution gas drive reservoir with a big aquifer influx also, the recovery can go as high as 49%. But definitely it's not only the water injection that has helped us, but the polymer flooding. Polymer flooding has also helped to increase a substantial recovery. Now coming to the second field. So I was telling that there are different methods of secondary recovery, that is gas injection is also. So I have kept this example where water injection and gas injection both were implemented. So as you can see, this is the line basically which represents the gas injection part, and this particular part is represented by the water injection. So in this particular period, water injection and gas injection both were implemented, and you can see there is a arrest in the decline. Why I am saying that, if I draw a trend line from this particular part, it should have followed this line. But after the implementation of water and gas injection, this decline has been arrested. Even though it is declining, but the decline is not that high. After the time we have stopped gas injection and we started only water injection, you can see how the water pressure response has been taken as it. So the reservoir pressure has increased, and it is also linked with the recoveries. So if you can see the circle, this particular circle, and if you can see this the red curve, you can see the reservoir are producing in a range of 100 kiloliters per day, but it has swept some oil and it has reached to a level of around 300 also. Even though there are some contributions of infills also, because if you are doing injection, you need a tapping point. If you are sweeping a while, by virtue of water injection, you should be having some tapping points to tap that oil. So infill is definitely required. So you can see the level of rate, oil rate basically, it has gone up. And the most important factor is the recovery factor. That is also substantial, 35%. So these two fields in oil India Limited has there are several examples, but these two examples have been shown to you for real field experience where water injection has really worked, and we have gained both in terms of reservoir pressure as well as oil recovery factor. It's a basically similar illustrations of in terms of cumulative oil recovery. Just to illustrate, this is the where water injection has been started, and this is the additional recovery till date due to, you can say, due to IUR. Now coming to the last slide basically. So water flooding can result in significant additional incremental oil recovery in many reservoir situations. I think in the last two well examples we have seen, and not all reservoirs are prime water flood candidates. So I have shown two important elements, that macroscopic as well as microscopic. So both these things should be taken care of while selecting a particular reservoir for a water flood. And the micro scale features may control the effectiveness of water flood, whereas if you look on the micro scale, that the mobility ratio is dominates basically. So with this, I have come to the end of the presentation, and if you have any questions to me.
Thank you, Dr. Manish. It was a nice presentation. Any queries from participants?
You can ask any questions from the presentation for water injection or elsewhere also. If you have very good.
I have a small query, Dr. Manish. So
Yeah,
I
yeah.
want to know what is the salinity of the formation water of the upper Assam basin, mainly the oil in
See, in Upper Assam basin, where while India is operating, basically it varies on age basically. So if I see Tirpam reservoirs or Bareil reservoirs, the salinity is below 2000 ppm. But if I go deeper in Eocene reservoirs, the salinity is in the range of 3500 to 4000 ppm.
and what is the range of the salinity of the water that we are injecting?
The water we are injecting, mainly it's in the range of around 200 to 500 ppm salinity water is being injected currently.
It is mainly formation water or the borehole water is injected.
We have got shallow water injection wells are available. So shallow water injection wells are basically being catered, but not all. Some produced water is also being treated and try to maintain a salinity. So I'm just giving you a rough estimate.
There is one query from the participant: why water injection is important?
Okay, so I think In the field examples, let me go back to the previous slides. I think this slide has answered your question. So I will replate it. There are two important aspects of water injection. The first is the maintenance of reservoir pressure, and the second thing is increase in recovery. So you can see if you come to the black curve, you can notice that when the water injection is initiated, there is a arrest in reservoir pressure decline, and after that there is an increase in reservoir pressure also. So the first purpose is solved, and the second thing is increasing the recovery factor. So you can see the recovery factor after water injection is quite close to 35%. So both the purposes are being served this particular reservoir, and this is in general purpose of any water injection reservoir.
Any other queries? If there is none, we come to the end of this session. So on behalf of everyone, I want to thank Dr. Manish Kumar for sharing with us your knowledge and expertise on the very important topic of water injection, which is a very crucial part of the upstream petroleum technology. I believe everyone enjoyed your presentation, and it was a pleasure speaking with you. So once again from Dibrugad University, thank you, Dr. Manish. Thank you very much.
Thank you, Dr. Furkan, for accepting my request for accommodating in a very short interval of time. And I thank Dibrugarh University for giving me this opportunity to talk in front of so many persons. And I wish all the attendees all the best. And thank you once again.
Thank you. It was a pleasure. Thank you. So our next session starts from 4:15. From 4:15, we start our next session. So the resource persons are from Anton Park. They will be speaking on nanofluids and also the petroleum rheology. So please join me again at 4:15.
This conference will now be recorded.